So, now we are going to go back to today's topic of work done at constant temperature. Okay. So, and single and multi step work. So, let us talk about, we have defined, we have already discussed about how to calculate the work, and by definition work is minus P external dV and integration of that. Why we do integration? Because integration is typically used when we have smaller changes, we have many changes, otherwise we can also sum, right. So, this is a general definition. W is the overall work. We can, if we write an infinitesimal work, then we can always write dW is equal to minus P dV. This is for infinitesimal amount of change in the volume, and this P, even if I do not write, it is always the external pressure that we are considering. Now, let us see what happens when you go from one point to another point. Let us take 2 points. This is, let us say, P and V, and let us say this is P1 V1 and this is P2 V2. Okay. Now, let us say we go from P1 V1 to P2 V2. Okay. So, so you can imagine that process as I have a system of full of gas. We have discussed that before actually, and let us say I have mass M1, which is our P1 system, and we are going for, let us say we are going for higher pressure, right. So, I increase the mass and my final system will be a compressed system of much larger mass M2. Okay. So, M1G will be correspond to P1 and M2G will correspond to P2 and much smaller volume. So, this is the process that we are looking at, and we want to go in one step. If we go in one step, then how much will be the work done in that case? I said that we have to consider always the final pressure, because that is the pressure in which the system is going to go and equilibrate to. So, my external pressure actually, since I changed to M2, my external pressure is P2. So, now work done in this process is minus P2 V2 minus V1, right, because that is a final state that we are going to reach, P2 and V2. Remember, when we are in P1 V1, we is a properly equilibrated state, and we change to P2 at t equal to 0, and that time we create a non-equilibrium situation. Thermodynamics cannot handle that situation, right. We wait for the system to equilibrate. When once it gets equilibrated, it reaches an equilibrium value of V2, and then we see that how much work is done, we calculate that, and when we do that, it is minus P2 V2 minus V1, correct. How does it look if I plot it in the graph? This is the shaded region of the curve. Okay. Minus sign is due to the fact that it is the work done, so of course, minus and plus does not matter, we are always considering work done on the system, right. Now, W, since V2 is less than V1, our W is actually a positive quantity. So, that means we are doing positive work on the system, we are doing compression, right, that makes sense. So, this is the work done, this is the work done, the shaded region is the work done on the system that we have plotted. Now, instead of one step, let us break that process into two step process. Let us say we do not go to from P1 to P2 directly, we want to take one more step in between, let us call that P3 V3. So, let us say our P3 V3 is somewhere here, we call that P3 V3. Now, in that case, how much is the total work done? So, now our W has two steps, W1 and W2. For the W1, we go from P1 V1 to P3 V3. What will be the work done? Minus P3 V3 minus V1 okay, minus P2 V2 minus V3. Okay, acceptable? Now, let us draw that graphically and see what we get. We get this region and we get this region. Now, we get the red part of that. Now let us say the first one we call that as our W A, and let us call that W B. Now, is W A bigger or W B bigger? Look at the graph, which is bigger. So, W A was the black shaded region, W B is the red shaded region. So, W A was bigger and W B is smaller than W A. Okay. So, you see that instead of going in one step, if I take two steps, the work done on the system. So, in order to achieve the same state, the work that is required to do is smaller. Is it clear? Because we are going again from P1 V1 to P2 V2. Instead of going in one step, we have now taken two steps, and by taking two steps we realize that the work done is less compared to if we had taken one step, correct. Now, let us take a third step. Let us call that P4 V4, which is in the green region, and P4 V4 will be all that green region. Now, let us call that WC. Now, what do you think that WC is? You see, in the WC, this region, there is no work there in that region, right. So, WC is even smaller than WB. See, we went from P1 V1 to P3 V3 to P4 V4. I will just show that. From P1 V1 we went to P3 V3 to P4 V4 and to P2 V2 in 3 steps. And so, as we go more and more step, what we see is that work done getting less and less, right. Now, let us delete this particular part. Let us go try to take many more states from P1 V1 to P2 V2. So, let us take a very small amount of step, we call that, I will use a different color. We take a very small amount of change in the pressure from P1 to, let us say, P1 plus delta P, which will be a little bit increase in the pressure, which will decrease a little bit of volume. So, that state will be here, right, and we will get this much amount of work, right. From there, let us go to a little bit more this step. So, it will be this much amount of work, and like that when you go, we are going to go so, you see, as we are increasing more and more number of steps, the work done that is there, that is required to achieve the same state P2 V2 is getting less and less. Because remember, what was the first step? The first one step work was this much, all under the green curve, but now using many steps we are reducing that this amount of this place, we are reducing this place work, we are reducing. Now, instead of taking now finite number of steps, let us make infinite number of steps. What is infinite number of steps? Where you change P1 to very insignificantly small value of P1 plus dP, 2 dP, 3 dP. Once you do that, you will realize this kind of graph, and you can understand that that will be the least amount of work that is required to get to the same system, right. So, an infinite step will require least amount of work. Another thing that you can notice in this constant temperature work is that when we go in one step, let us say from P1 V1 to P2 V2, we try to go in one step. So, when we try to go from P1 V1, let us call that A and to B, work done going from A to B was minus P2 V2 minus V1, right. Now, let us go back. So, we went from A to B, now let us go back from B to A. What will be the work done? Minus P1 V1 minus V2, correct. Now, if I rewrite this equation, or let us say we just only consider the magnitude of the work, then the sign will not matter. I will just write with the sign now P1 V2 minus V1. Now, let us take the magnitude of the work. So, now magnitude of the work W A going to B will be P2 V2 minus V1, and this one will be P1 V2 minus V1. Now, this is P and this is V. Now, we know that P2 is larger than P1, therefore, W A to B is greater than W B to A, the magnitude of the work, right. Why we have to take the magnitude? Because in one case it is work done on the system, it is another case work done by the system. That is why we have these signs. Signs only mean that, but the magnitude of the work remains the same, right. Whether environment is getting work out of the system, in that case it will be negative. Whether we have to work on the system, in that case it will be positive. It is either way, because we put the work in the system in order to retrieve it later on, right. We put energy into the system, either oil or some other piston or a spring. We compress a spring. Why? Because that spring later on will give us the work in terms of moving the clock, right. So, the direction, this positive and negative, is just to indicate that whether we are storing the energy or taking out the energy of the system. Now, you see, if I go from A to B doing some work on the system, when we come back from B to A, by doing the same amount of work we cannot reach. You understand? So, when you go from A to B and do some work, the same amount of work cannot bring us back from B to A. So, that is why this process is called an irreversible process. Right? This is an irreversible process because we have lost something. Actually, it is very different if you calculate that. So, if you just plot that, one work was this much. Sorry, I have to just in a hurry. One work was this much, another work was only this much. There is a huge amount of work that is lost just because of going in one step. Now, you know that U is always same between A and B, because U is a state function. So, delta U A B is a constant. So, now we know that delta U is work plus heat, and since work is so much different, the difference is coming because of the heat. In both cases the heat is going out, but in one case it is more and one case is less, and this has great implications. You will see later on the heat that is going out or coming in, whatever, the change, the amount of heat that is being produced in these processes are different because the work is different in order to keep the U same. U is a state function. So, U only depends on whatever pressure, temperature and volume the system has, and that has a fixed P and fixed V. For 1 mole of gas, therefore, temperature is fixed and U is fixed. That is we discussed last time, right. So, which means that if you do a one step work or even a finite amount of step work, you are going to be, you are going to follow an irreversible path. Okay. Now, let us see when you do a multi step work what happens. So, let us say we are following an infinitesimal processes, then how do we write the W? minus P external dV. You noticed one thing in this particular case, I have put the P external. So, W equal to minus P external dV is a formula, right. That is a formula that we are using, because the formula we are using, because dW is minus P external dV. This is the formula that we are using, right. And P, as you can see, P is not being varied, P external is just a value, whereas dV is the differential amount. So, we are changing the V. Now, interestingly, when you changing the V very, very small, P also changes extremely small way, and since P is changing a little bit small way, we can imagine that we are basically, what we are doing is that we are writing the total work done by changing the external pressure at every step of the way. I is the step that is taking us from one point to another point. Now, we know that whenever there are discrete number of steps, we do a sum, whenever there are infinite number of steps, we do an integration. So, essentially what we are doing, we are changing the pressure a little bit small amount and let the system equilibrate. As I said, the thermodynamics cannot deal with non-equilibrium system. I will give you one physical way of remembering this. Let us take a box of gas molecules, and remember earlier what I was having is a block of mass m, which could be replaced by another block, right. But imagine that instead of the block, now I have instead of the block I have sand, a pile of sand. So, I will gas molecules, I will put a circle now just to distinguish gas molecules as circles and pile of sands as dots, and that pile had a mass m1 giving rise to pressure P1, and now I am going to go to P2, higher pressure. What I am going to do is that in the next step I am going to add, in this pile I am going to add one more sand. Okay. It is very difficult for me to reproduce this particular picture, but imagine that I had exactly the same one and I put one more sand, and you know the sand is very, very small. So, I am changing the pressure extremely small and let the system equilibrate, system gets equilibrated, it gives me a different volume. Then I add one more sand and one more sand, and that way I am taking the system extremely slowly from P1 V1 to P2 V2. If I do that, then I can say that since I am doing multiple steps, I can write now sum as an integration, and now we are going to evaluate this integration. So, W is minus P external dV, that is, and a P is now within the integral because P is also changing along with the V. Now, we know that from ideal gas system that PV equal to nRT, right. So, our P is nRT by V. So, I am going to replace that here, and it is a constant temperature process, I told you, right. It is a constant temperature process because whenever you are changing your P, let us say you put one more P, what is going to happen if the volume remains constant? If the volume remains constant, if you increase your P, your temperature is going to increase. Now, volume changes in order to adjust that. So, but if you do not let your system to exchange this extra heat that you have had in the system because of the pressure. So, ideally let us say the system is static, it is an isolated system, you put the more pressure, what is going to happen? Temperature is going to increase because there is no way to release the heat. But you know from zeroth law of thermodynamics that if two systems are in contact with each other, they will become in thermal equilibrium. So, ideally in order to keep the temperature constant, what is done is that you have a reservoir of a particular temperature. A reservoir meaning is like a sea, in which in the sea if you put some ice, let us say the sea's temperature is 20 degrees centigrade, you put a ice of 1 kg, what will be the temperature? 20 degrees centigrade, because the amount of water that is there is very difficult to change the temperature of. And if you let us say put some boiling water 1 kg, what will be the temperature? 20 degree. So, that is called reservoir. Reservoir is so big and at a particular temperature that it can supply energy and take out energy without changing its own temperature. So, what is happening is that whenever you are changing your pressure, you are increasing the temperature that or heat the system, that is taken away by the reservoir, by the cold reservoir or whatever is kept at that time, by the same temperature reservoir, and that allows the volume to change. Because unless the temperature is constant, the volume is not going to change, right. It is very important to know because how the process is going on. Now, equation wise is very simple. So, since our temperature is constant, we can always write P as nRT by V, that I have written. Now, since temperature is constant and R is constant, I will write RT as outside and N also outside. Now, I have dV by V going from V1 to V2. So, minus nRT ln V2 by V1. So, that is the isothermal work done on a system. Now, you see, since V2 is less than V1 in case of compression, this quantity is negative and negative will give you a positive work. If it is an expansion, then ln this term will be positive and therefore, we will get a negative term. Now, this is when we are going from V1 to V2, that means A to B process. Now, let us see what is going to happen when you do the reverse one. Then you also write the same thing, P external dV, you write nRT by V dV minus nRT dV by V. Now, you are going from V2 to V1 minus nRT ln V2 by V1, sorry V1 by V2. Now, this was work done from A to B, this is work done from B to A, and we can see that the magnitude of the work done going from B to A is exactly equal to magnitude of the work done going from A to B. So, if I do the process extremely slowly, then it is called as a reversible process, which means an irreversible process will do two things. If we have to compress it, we will have to do minimum amount of work, and correspondingly if the system does the work, it will do the maximum amount of work. That is what called maximum work done, and you will see later on that maximum work is possible because the process is done in a reversible manner. We call it reversible manner, but you should know that ideally nothing is reversible, because we are talking about an ideal gas, but when you compress, even if you put a sand and all, the piston is connected to the container which has some friction, that friction will create some heat and therefore, you are going to lose something. So, therefore, nothing is reversible practically. So, but the closest to a reversible is called quasi static. So, we are actually going almost as slowly as if it is static. However, it is not static because we are changing it. We are changing it extremely slowly, one point to the next point to the next point, but we are doing such a way that it looks almost reversible. So, therefore, it is called quasi static process. So, a quasi static process is process in which the things are changed very slowly. So, that we can show the same thing here. Yeah, I have said the same thing, that maximum work is done by the system if the expansion from V2 to V1 is done by infinite number of steps, i.e. reversibly. Since the reversibility cannot be achieved in real life, this kind of infinite slow processes are termed as quasi static process. Values obtained from quasi static and reversible processes are taken to be same, here. Now, just for your own this thing, can you tell me that what will be the work done for a free expansion? You know what is free expansion? Free expansion is where there is no external pressure, therefore, it will be 0. So, work done for a free expansion is 0.